Okay, so here we are in Math 2265, and we're going to be switching books mostly. I'll still have the first book around, including today, but we're going to lean more on the somewhat easier text of the newer book, which you find in the syllabus. And some of you undoubtedly have been using already, so we encourage you to shift gears and go over to that part of it where you'll find it to be quite a bit easier, although there are a few small disadvantages I'm finding. I guess a couple of comments on the test first of all. I had the four classes, which are all the same, Math 1101s. They all, well, 99% of them put their answers on Blackboard. And certainly some of you guys did too. And I think part of the difficulty was when some people didn't do that. That causes a bit of a strain on me. But yet, how do you do a box plot on Blackboard? So some people ran with that and thought, okay, I don't have to put any answers on Blackboard. And that's not really true. But then perhaps I wasn't especially clear. I just assumed that everybody would put as many answers as possible on Blackboard, which many of you did. But there were certainly a large number of people that put little or no answers on Blackboard, which, as I've been doing a pre-check before I look at your PDFs, caused a lot of zeros to show up at first. Well, they mostly got corrected after that, but anyway, I think I employed a rather generous curve. I don't know if anybody will complain about that, but if your grade is, needs to be changed, from an A down to a B, I'm willing to listen. I don't get too many students asking for that, though. But anyway, we'll try to be clearer as to what to do about Blackboard next time. There will be more multiple choice, which of course is far easier for me and not that terrible statistically speaking as far as measuring students' knowledge, although it's not as good as showing their work in a particular problem, obviously. So we'll have more of a balance that way. And then I'll be clear as to which ones I do not expect to see answers on. But as a general rule of thumb, I at least want to see the answers in Blackboard and the work on the PDF. Ideally handwritten, although a few of you do such a great job in typing that I can't complain very much. But mostly it's just meant to be your handwriting. I'm assuming it's halfway readable, and I don't have great handwriting, so I can accept it up to a certain point. But anyway, certainly if you have any questions on the test, let me know. Office hours are a good time, or email. That would be good too. So meanwhile, I'm going to kind of recover what we did last time about the confidence intervals, and I'm not happy with the titles of these sections sometimes. But this is going to be, well, the title of the chapter is confidence intervals. Maybe you can see it on the far left here, but the sections are talking about the confidence intervals CIs with respect to a single population mean using the Z, the normal distribution. And yes, I do want to get into 8.2 where we look at it from a different perspective. It's called the t-distribution, which has the same shape. I'll show you some pictures from our original book that looks really almost indistinguishable, but we'll point out any minor differences there may be. And it's funny how the z, the normal distribution, dominates the landscape of distributions. And then the number two distribution, without a doubt, is the t-distribution, which looks very much the same. Well, we'll get to that in a little while. But now I'm going to be going primarily from the other book, OpenStax, I think it's called. And let's see if we can read some more detail here. A CI, which I'm always going to say, for a population mean, when the population standard deviation is known, is based on the conclusion of the central limit theorem, which we can talk about briefly as well. In fact, why don't I do that? Why don't I just take a quick look at it? We don't need to have a very long look at it, but as I click on that, let's just see the result, which I've already advertised. Don't need so much of the theory, but essentially it's going to replace sigma by sigma over square root of n. Now they're using the x notation subscript, which is, I don't know if that's completely necessary, but the point is you got to get that square root of n in there. So it's what they call complex fraction. You could actually put it in the numerator, but nobody ever does that. So the idea is to find out what this number is. It's got a life of its own. And it's actually called the standard error of the mean. And this has a way of incorporating sample sizes n. So yeah, when you're drawing them from a sample and you know that the standard deviation is known, which in real life is a bit rare, but it does happen. And then you can scale it downwards by putting that square root of n in there. And they're saying the same thing in a different way here. X bar is normally distributed, the capital N, very popular, along with mean. The mean is not changing. That will stay the same, but the standard deviation does shrink down because the sample size And I was demonstrating in my overview class that if n gets very large, this standard deviation gets very small, and you get much more precise estimates, which is a good thing. So you have incentive to get a large n, but mostly in these problems, you won't have a choice. You'll get whatever they tell you it is. And this book is heavily using the TI 8384 calculator. So if you happen to be already doing that, fantastic. If not, well, okay. They do show the algebra a lot of the time. And so, this is just an example. They're shifting gears, by the way, from x, a single value of x, to an x bar, a sample mean. I guess I didn't make that very clear. This is why people read all the theory, I suppose. I'm sorry. But x bar could land between 85 and 92. And it's a little bit more tightly bunched if you have samples even of size 25, which is considered kind of a smaller sample. And one could actually find that probability. They lean heavily on the TI, and they type in the maximum, the minimum, the maximum, and then of course the mu and the standard deviation, which has been adjusted. It's no longer sigma, it's sigma over square root of n. And this would be super easy to do. 15 over 5, that's 3. But if there's any doubt, you could just type it in as the SQRT and all that and get the exact answer that way. Or you could put a rounded number in, but then you'll get a rounded number back too, which is slightly weaker. So anyway, don't really need to cover this per se, but it is traditional to cover this. But really the bottom line, as I say, is if you're switching gears from x to x bar, the sample mean, and you have a sample of size n, then you have this adjustment to be made due to the very famous central limit theorem, which does have a ton of theory associated with it. By the way, if n was 1, then the x bar would be x, and hey, it would be exactly the same as before. So if you have an individual score, say a sample of size 1, then you have no change as to what we taught earlier. So there you go. Okay, let's move back to the main subject, kind of a recap of what the heavier book talked about before. Okay, so they say that, well, they have this dialogue here about the EBM, and I don't like it when books spring something on you without even deciding what they've told you what it is yet. So this seems like it's been written out of order. But the constructed confidence interval for a single unknown population mean mu, where the population standard deviation is known, and you have to get started somewhere, so it's a good place to start. And it does actually happen. I've been there. It does happen. It's a bit rare, though. We need x bar as an estimate from mu, and so that's what it's going to do. It's going to pinch hit for the actual mean, sample mean for the population mean. And we need to know a margin of error, and there's formulas for this. They're going to call it not M or E like most books do, like capital E for error, not little e, of course, or M, whether small m or big M. But they're going to call it EBM. Every book has to be different. They've got to carve out their own little niche. I don't know why, but they do. And it's called the error bound for a population mean. Okay, very nice. EBM. Okay, whatever. I'll have to try to remember that. The sample mean, x bar, is the point estimate, a single number. It's actually a very easy topic, although the other book made it seem rather difficult, even though it is a relatively easy topic. And as we saw before, you basically take your point estimate and add and subtract the error bound, or the error. So x bar minus and plus the error. And that gives you confidence interval estimate, and there's a confidence level that we saw. Mostly it's 95%. Sometimes it's 90, sometimes it's 99, even occasionally something else. And we can talk about that too. TI would find that rather quickly. And it's the choice of the person constructing the confidence interval to choose a confidence level of 90% or higher, which is virtually always the case. You just never see, they never bother with 80% confidence intervals. The person wants to be reasonably certain of their conclusions. So yeah, 80% isn't so reasonably certain anymore. And we have this other probability called alpha, which I kind of mentioned is kind of the dark side of the confidence level. It's the non-confidence area, for lack of a better word. And it's the probability the interval does not contain mu. In other words, you take your confidence level, say it's 95%, and you add that to alpha, and you will get 1, because they have to add up to 1. And that means alpha would be 5%. With 95% confidence, alpha is 5%, mostly listed as 0.05. And it's a kind of a weird tradition that the confidence level is done in a percentage, and alpha is almost always done in a proportion, a decimal. No accounting for taste, that's just what happens. It shouldn't confuse anybody. Here's an example. The book does have a few examples, maybe not as many as the other one, but it does have some. And suppose we've collected data from a sample. We know the sample mean, and we don't know the mean of the entire population. The sample mean is 7, and the error bound is 2.5. So this is a very simple one. Simply add and subtract 2.5. You obtain 4.5 up to 9.5 in interval notation, and you could say more formally that we estimate with 95% confidence that the true value of the population mean is between 4.5 and 9.5. Well, yeah, okay. Here's another one. Data from a sample mean is 15, error bound is 3.2. And all you'd have to do is subtract 3.2, that'd be 11.8. And then you could add and get to 18.2, and that would be your bounds for the confidence interval. Okay, for a population mean, there we have the confidence interval, and there's a known sigma based on the fact that the sample means follow an approximately normal distribution, and maybe the mean is x bar is 10, and somehow we need a 90% confidence interval, and the error is 5, so they've added the 5 and subtracted the 5, which is just from 5 to 15. To get a 90% confidence interval, we must include the central 90% of the probability of the normal distribution. Yeah, so we go to the middle part, middle 95, middle 99, middle 90%. And so we would leave out a total of alpha is 10%. That's kind of the non-confident area. And we divide that in two because it's always symmetric for the two tails. And 5% would be in each tail. So yeah, you got 5% on the left tail, 90% in the middle, and 5% on the right tail. Not too difficult. Okay, so to capture the 90% in the middle, we must go out, as we saw earlier, 1.645 standard deviations on each side of the calculated sample mean. The table would show you that visually, and plus and minus 1.65 has a bound of 97.5% minus 2.5% for a total of, well, actually I made a mistake here. That would be, what, 95% minus the 5%. Then you get your 90. Yes, so the 90% is 1.645. The more usual one is the 95% with 1.96. Okay, let's see here. It's important that the standard deviation used must be appropriate to the parameter we're estimating. So here we need to use a standard deviation that applies to the sample means, which of course is sigma over square root of n, and also known as the standard error or standard error of the mean, even SEM. I've seen that abbreviation too. We can distinguish clearly the standard deviation for a mean of the population standard deviation. So we have said all this before, and they're just reiterating the center limit theorem, the key parts of it. So now to calculate the confidence interval, we need data from a random sample, and the steps to construct and interpret them are calculate x bar. If it's not given already, you would have to calculate it. And we would already be given sigma, so that's a nice thing. We get to use z as well. And we would find the z-score that corresponds to the confidence level, 1.645 for 90%, 1.96 for 95%, and 2.575, depends on the book, for the 99% confidence interval. Sometimes it's 2.76. We'll see what this book has to offer. I haven't actually checked that. And then find the error bound and construct the confidence interval by adding and subtracting. And then you could, if you'd like, write a sentence that interprets it in the context of the situation. So finding the z-score, here's the one that's the big one. They go into a little bit of detail here. It may be slightly tedious, but man, to me it's so refreshing to see it done this way versus assuming you already know it. It's like the other book assumed you already had statistics. And if you have, great. But if you haven't, oh, okay, now what? But anyway, we need to find the value of z. It puts an area equal to the confidence level in the middle of the standard deviation. So we're going to eventually get to the 95%er here. And so the confidence level, by the way, from that little formula we had before is 1 minus alpha. So that's another way to look at it. So if confidence level is 95%, 0.95, then alpha, of course, is 0.05. 1 minus 0.95 is 0.05. That would be the area split in half. And this time you split the 0.05 in halves, and you get 0.025, 2.5% in each of the tails. So focused either on your calculator if you have a z alpha notation, or even the table, you could find that this would correspond to a negative 1.96 percentile-wise, cumulative probability-wise, And the one on the high side would be a positive 1.96. Of course, it's symmetric, a big advantage of the z and t and several other curves that are symmetric. And by the way, the inverse norm command would give you that z value. And so you could type in the area to the left, and that would be, so 0.975 would be the first one given, and then 0 for the mean and 1 for the standard deviation, and you would have your z value from that way. So area to the left of z, I really don't have the capacity right now to draw a picture, but that would mean that you have only 2.5% left to go, no pun intended, but the cumulative value would be 0.975. Area left is what I always say in class. And this is the cumulative value. But you get that by noticing all of this. The alpha over 2 and 1 minus alpha over 2 is what you would actually have to calculate. Calculator won't do that for you unless you have some other brand that I've not actually heard of before. Well, anyway, we have the error bound is just the z value times sigma over square root of n. And that's going to be what you add and subtract. And so they go through a little bit of algebra here, showing the alpha over 2's, and then the 1 minus alpha. The sum, of course, adds up to 1, as it must always do with a normal curve. And yeah, they have a formal write-up here. I'm not quite so formal as this, but it's never a bad thing to do this. And so state the confidence level, explain what the parameter is, and state the confidence interval. We estimate with so-and-so confidence that the true population mean is between so-and-so and so-and-so. And you could include units, which is never a bad idea either. Okay, suppose scores on exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. And a random sample of 36 scores is taken. I love it when they pick nice, perfect squares for your n, but they don't always do that. Gives a sample mean of 68. So we can use the 68 in other situations to find a confidence interval estimate. And we'll like to find a 90% confidence interval where we'll be expected to be correct 9 times out of 10, 90 times out of 100, and then be incorrect 10 times out of 100, 10% of the time. That results in a narrower interval, which is good, but of course, then you're 10% likely to make a mistake as well in the long run. So let's take a look, and they are using technology, which they'll do in a minute, but for now, we notice what the sample mean is that's handed to you. We can find the error, EBM as they call it, and Z from a 90%er will be 1.645. We just stated that before, and that is also known as 5% to the right. This is to the right notation. Your calculator would have to say 0.95 for the area, the cumulative area. So these notations are almost fighting each other. I've never been a fan of that. Never been a fan of the Z alpha notation, but it's something I can't get rid of. It does have some conveniences, but as far as the TI and other purposes, you'd have to actually use the cumulative value instead. So yeah, that'd be up to 0.95, leaving alpha over 2. And of course, let's say this alpha is 10%, 1 minus 90%. Cut it in half, 0.05. You can use the Z notation, or on the calculators I'll show you in a minute, it'll be the 0.95 number, cumulative speaking. Okay, so that's 1.645. And then the other numbers are quite routine. 3 over square root of 36. That's going to be 3 over 6, which of course is 1/2. Half of the 1.645. And that's going to be 0.8225 added and subtracted, yielding our confidence interval for the standard deviation and the n. And it's a pretty tight one. Usually when you take samples of any size at all, it tends to narrow down the interval even more dramatically than just a 90%er would. So here's the calculator steps, and stat, tests, Z interval, enter. And by the way, I always love it when people show me what they did. I just love that. And when somebody comes along perhaps and then doesn't show me any steps, I get a little offended actually. So as a general rule, give me a little hint as to what you did. Maybe you don't have to give me the very first step or something, but give me the main stuff. Tell me you were in Z interval, and tell me what you did, the C level command. Tell me how you did it. Now, my calculator is a little bit older, and it makes you do it. It's in parentheses style. Perhaps you just have to answer the questions. And so just tell me what they were, and then tell me what you got. And that couldn't be easier, I think. But I do know get a certain number of students that are very offended with having to show any kind of calculator steps. I'm sorry, this is just what we have to have you do. And so maybe in the future you'll never have to do it again, but in a class like this, we will need to have a little bit of documentation. And oh, by the way, if you're interested in partial credit, that would be vital for that kind of a thing too. Anyway, so they would give you the same answer, of course, and round it to perhaps 3 decimal places. I'm not quite sure how that would go. So same thing could happen here. The same z-score, 1.9645, would be used. Or if you're using the calculator, you'll type in 0.95, and you'll have to find the standard deviation, which would be, well, the mean's 36, and you'd have a random sample. And there's the standard deviation. There it is, 6. That'd be divided by the square root of 28. I'm not going to work that one out, but you can see how it matches pretty nicely the last example. So this one is just a list of data. I'm not usually a big fan of these because then people with the technology have a huge advantage over those that might not be doing that. And I've never found that to be productive on a test. Now maybe on a homework assignment, sure, it doesn't make that much difference on the grade. But yeah, I can't assume that everybody is using the TI or equivalent like a Casio or something like that. But keep in mind, standalone non-cell calculators are perfectly okay. But cell phones are not okay. And I think it's obvious why. If you are really confused by that, let me know and I'll get back to you. But, if it's standalone, then there's no communication going on. If it's not standalone, then who knows who you're talking to? That's known as cheating. So anyway, we're not going to allow that as best we can. So here's a 98% confidence interval. That's going to change a little bit. You'd have to notice that alpha is 2%, leaving 1% in each tail. Don't have the benefit of a sketch right now, but then you'd have 0.99 put into the TI, or you'd have to look up the values on the table, and I don't happen to remember what that is right at the moment. I should have that memorized, but I don't. Let's take a look at what they have to say here. Now, of course, here you had to dig around for the mean and standard deviation, so that's always going to be a setback, but looks like here we had the standard deviation. Okay, that's a given, so you don't have to calculate that because these are sigmas known, 0.337. And according to what they're telling us, it wouldn't be very hard to find. The x-bar is 1.024, and I can't remember what they're measuring. The specific absorption rate for a cell phone is the amount of radio frequency energy absorbed by the user's body when using the handset. And some are higher and some are lower. Okay, whatever. Okay, so we're looking at a 98% confidence interval, which, as we stated, was 1% in each tail. And they're focused on the right tail. They're using the Z notation. Now, of course, the TI will want to use the left-facing material, the cumulative material. But either way, we can, not too difficult to find the Z value. Now, TI would avoid this kind of thing. So I guess I reserve the right to ask you to show algebra steps. Now, will I do that a lot? Probably not, no. But I guess I have to reserve the right. So I'll get a little bit clearer as to what I might intend to do. But I'm a firm believer, because I've taught this class using algebra for so long. And then the technology, I'm not going to say it eats away at that, because it's definitely a big plus. But I'm still a fan of algebra. I still intend to use it sometimes at least. So, and this is not a difficult case. So this would be one of my first choices, to ask you to please use some algebra. And then you can double check it on your programmable calculator if you'd like. And I would highly recommend you do that. Well, anyway, that's Z value, which they've gone to 3 decimals on. They sometimes go to 2s and sometimes go to 3. 2.326. And then we have our standard deviation, which was given, divided by the sample size square root of 30. I don't have all those details, but it does work out to be 0.1431. And they only had 3 decimals here and 4 decimals there, a little bit of a disconnect, but hey, whatever. And so that means our confidence interval will be between roughly 0.88 and 1.17 watts per kilogram. We can estimate that with 98% confidence that the true mean for the population of cell phones in the US, which is a sweeping statement, is between these two numbers in terms of watts per kilogram. Now, of course, the TI would go and find out various other things. If it's a C level that you need, then it's easier. You just type in the 98%. So this one might be a different model where you don't have to divide it in 2 and you don't have to worry about that. So I wonder if I misspoke earlier. I don't think I did. I'm just going to check that earlier, because if they just say C level, then there's no need to find an alpha over 2 at all. But the calculator I have does need it. So just check which one you have. And yeah, here they seem to, yeah, with inverse norm, you have no choice. You have no choice but to do that. But for the other one, apparently they're being more flexible with the newer models. My model is like, 10 years old now, so it's an antique. Okay, so we can continue. We find our confidence interval, and so the Z, it makes it very, very easy. You just type in your sigma, you type in your n, you type in your x bar, or perhaps you had to dig that up from some other process. And at least in this case, you would never have to find sigma because that's supposed to be a known value right now. And so we have another table. I don't know if this is the same data or not. 1.48 was the first number. Well, I guess they've just limited it a little bit. And this is one that you could try if you'd like to see how it goes. Okay, so this time they were looking for a 93% confidence interval. So you would have to find the Z value, or if you're using a TI, then you would not even find that out at all. It'd be somewhere around a 2, but I don't have that on the tip of my tongue. That would be a rather rarely used confidence interval. I would say that 95 is the king of all of them. 90 and 99 are tied for second, but fourth would be 98%. I have actually seen 98% used a few times. But all the others, 91, 92, 93, 94, those are rarely used. But with a TI or with an equivalent calculator, don't have to worry about it. Okay, so we now changed it to use a 95% confidence interval. And so everything is the same, except it's a 95%er. And showing it by hand means that our value, this is going to be one that you'll for sure memorize because it's just a very, very common number in statistics, 1.96, occasionally approximated as 2. And they actually found it by using inverse norm, or you can just find it by looking at a table. But this is just one that I've memorized because I've used it literally thousands of times. 95% being the major confidence interval, and z-scores being important, even though the TI doesn't seem to think it is. You can find the 1.96, which is instrumental in carving out your confidence interval. And I think it's a good idea to do it by hand, so you have some kind of appreciation for what the technology is offering you. Okay, by the way, because it's 95%, it's a larger margin of error. We only had 90 last time. Now it's 95. So this is going to be a little wider. And so that's 0.98. Before it was like 0.8 something. So now the interval is wider. They even have a comparison. This one was a little bit tighter with only 90% in the middle. The one we're looking at now has 95% in the middle, much more popular actually. And now our interval, well, see, doesn't change that much, come to think of it. The older one was 67.18, and now it starts at 67.02. So not much difference is there. And the last one ended at 68.82. The new one goes all the way to 68.98. Oh, wow. It's a 0.16 difference on either side. So, sometimes you can't hardly tell. And other times it's quite dramatic, the difference. Depends on what the data is measuring and how big the numbers are. But yeah, for 99%, it'd be wider even yet. I've been fond of asking questions that ask you to do all three of them, because once you get the hang of it, doing it a couple more times is not a big deal at all, and you can see it actually getting wider. So increasing the confidence level, confidence interval, so to speak, increases the error, makes the interval wider, of course, and when you decrease the confidence level down to like a 90 or even an 80, it decreases the error and makes the interval, of course, narrower, kind of intuitive. And they do have one about the pizza. I've got my cat here now. They'll meow at me for a while. And anyway, let's take a look at this example. I do want to get over to that t-distribution at least briefly today. So let's see. This is what happens to the error bound in example 8.2 if the sample size has changed. Leave everything the same except the sample size. So let's take a look for the sample size. We're back to 90% first of all. That's important. And we have the fact that we're back to 90%, which means our Z was down to 1.645. But I think before we had 36 in the sample. Now we're going to get more precise and get a bigger sample. Everything else stays the same, but our bigger sample has an effect. The 1.645 is exactly the same as that first example. Sigma, of course, is still 3. Now we're going to divide by a bigger number, and it's getting larger. I pointed this out in my 1101 class earlier today, in fact. And the That's going to be 3/10. Before it was like 3/6, which is a half. So this is already decreasing by quite a lot. And now our error is 0.4935. It's getting tinier than before. I don't recall the exact number before, but I know it was quite a bit different. And if I can find that really fast, it's a disadvantage of wading through all this stuff. Well, I can't seem to find it. It's going to take too long. So anyway, it has changed. We have a bigger sample size, so we have more precision, and that's a good thing. That's a good thing. So we're down to a lower error and a tighter, smaller, narrower interval, which is always good to be more precise. So we bring up n up to like 1,000. It's even better than that. And in my other class, we did a sample size of 100,000, which is hard to believe, almost never happens. And then we had very tight errors, very tight intervals. But they've already moved on. They're already moved on to the next subjects. They only get an overview where you guys get to let it sink in a little bit more, especially since I'm kind of covering this section twice, because I think this is quite a bit more readable than the last one. But if you understood it last time, this might seem a trifle redundant right now. So increasing the sample size is a good thing. It causes the error bound to decrease, the error decreases, and makes the confidence interval narrow. That's a good thing. I'd like to put a star on this, but I can't seem to do that. And then if you decrease the sample size in order to save money or get a deadline pushed through, then your error will increase and the confidence interval is wider. Not quite so precise. May not be the end of the world, especially if there's not much difference. And this is one that we're not going to use very much. I've seen this before in other books, but I'm just going to quickly, briefly mention it, but I really have no intention of giving you problems regarding this kind of thing. So usually you find the sample mean, calculate the error, and then find the confidence interval. But occasionally the study may only state the confidence interval. And so knowing that, you could work backwards to find the sample mean and even the error. So they show a few examples, and I'm not going to look at all of this. You can certainly skim through that if you'd like. But here's a given confidence interval. Okay, we'd like to find, first of all, the error. And so really all you have to do, and then they also said, you might know that the sample mean is 68, which happens to be exactly halfway here. And yeah, so that would be a way to find the error bound. You just pick one of these and subtract the sample mean away. And it doesn't matter which one you do. You're going to get 0.82 each time. And 68 minus 67.18 is exactly the same. It is symmetrical after all. And of course, your bound has to be positive, so don't give me a negative number. That's not exactly what we're looking for. Now, if you don't happen to know that 68 is the sample mean, you could basically subtract the two, find that extra wide width that the other book was very fond of. They didn't even like to use margin of error, which I found to be a bit strange. And then divide it by 2 to find half of that width, which of course is an error, plus or minus the error, EBM, as this book likes to say. Okay, now to get the sample mean, well, you could do it this way and get the 68. And so if you happen to know one of the endpoints of the confidence interval, such as the high one, which is a little bit easier to work with, and then you happen to know the 0.82, you just subtract them out and get exactly 68.0. Or you could just simply average the two. This is what I've done a few times. Just take the two numbers, average them, add them, divide by 2, and you get exactly 68. So that's in case of emergency, but I have no plans of doing that. This one, though, it looks like if you added that together, you would get exactly 90. How about that? So the mean is 45. Now, 45 subtracted from the 47.88 would be 2.88, and that would be your error bound. Okay, now we actually have formulas that calculate in. I think we might have looked at this briefly. If not, here's an explanation for calculating in. So sometimes we put these goals in front of us and we need to see how many people, how many subjects do we need to get at a minimum to guarantee these types of things, such as a certain percent of confidence or a certain error amount. So they depend on the z sigma over square root of n, but they, without showing a lot of the algebra, in fact none of it, they've solved for n already. And this is a little bit more readable than before, although I prefer to just say e. Capital E squared is good enough for me. Maybe this is somebody's initials who wrote the book. I don't really know, but they keep dragging extra stuff around. Hey, I'll get used to it. So z sigma over e, and then you can completely square that. So I'd really just say z sigma over e, quantity squared. Isn't that a little bit faster? Seems like it would be. I'm not even sure if this is available on your calculator, so at least I've never found it on mine. So anyway, take a look at this example. And at the age of certain students is 15 years. Wow, that's pretty young. So, oh, I'm sorry, that's the population standard deviation. Yes, okay, that's 15 years. Okay, now we want to be 95% confident that the sample mean age is within 2 years. The within number is the error. That's the E, capital E, or EBM if you wish, of the true population mean age. Notice we didn't say what the mean was. We're just giving you the error. The mean is nowhere found in this formula. Yeah, how about that? It's not there, so we don't need it. So just because it's not there, it doesn't mean we can't use it. We get so used to using the mean, or even n for that matter, that this is shaking things up a little bit. So I think it's healthy to do that. Well, for a 95% confidence, that magic z that we all look for is 1.96, z of alpha over 2. And using the formula, we put in that 1.96 and square it. We put in the 15 for the standard deviation sigma and square that, and then divide by the error squared as well. Or if you prefer, I think it's just a little bit easier to go 1.96 times 15 divided by 2 and then square the whole thing. We get 216.09. I think we might have mentioned this before because this is the minimum number. 216 is below the minimum. That means we do have to get to 217. We always round up to the next higher integer to ensure the sample size is large enough. Otherwise, you're not really 95% confident. We're like 20 or 94.98% confident or something. And statisticians pay attention to this kind of thing. I know some students don't, but that's what separates the A's from the B's some of the time. Hey, I hate to say it, but that's kind of true. Anyway, you got 217 football college students, or Foothill College students should be surveyed in order to be 95% confident that we are within 2 years of the true population mean age of those students. And here's another one. Here, standard deviation is 3, sigma is equal to 3, 95% confidence, z is 1.645, and the sample mean height is within 1, so E is only 1. So how would things change based on this last example? Well, we'd have our 1.96 squared, we would have a 3 squared instead of 15 squared, and we would be dividing by 1 squared, which is no big deal because the E is 1. That just fades out. So although I can't write it down, it's 1.96 times 3. I'll do that on my calculator right now. 1.96 times 3, and as I learned, just square that result, and you get 34.57 or 35. That one naturally rounds up, so 35 would be all you need for this one. That's surprisingly low, but then this standard deviation was a lot tighter as well. So that's why we have a relatively low sample. How about that? Okay, so now as I get over to 7.2, let's take a look at, 8.2. Sorry, we're in chapter 8 in this new book here, not new book, but the alternate book. And the title is The Confidence Intervals for a Single Population Mean Using the Student T Distribution. And so we have a bit of a story here. In practice, we rarely know the population standard deviation sigma. In the past, and I'm old enough to remember some of this, when the sample size was large, this did not present a problem to statisticians. So usually, and even the other book was saying, once you get past a certain number, Z is basically the same as T, and that is still true. And they used S, the sample standard deviation, which could either be calculated or could be given depending on the problem. So it's pinch hitting for sigma, and when n is large enough, there was never a problem. But problems resulted when the sample size was small. So our other book says that as long as it's greater than 30, it's approximately the same, and that's sort of an old school way of teaching. But because of the advent of calculators, T is used virtually every time when you have S. So T is starting to take over, at least in this mode, as far as the mean distribution. Now, if we have a story about William Gossett of the Guinness Brewery in Dublin. He was the head brewmaster. Oh, and by the way, he was the head of the statistics department at, I can't remember, was it Oxford? No, it couldn't be because this is Ireland, right? And I still have the Irish music playing in the background. I don't know if you can hear it. But anyway, he was head of the statistical department at somewhere in Dublin. I cannot remember the name of it right now. His experiments with hops and barley produced very few samples. I can just see him smuggling out bottles of Guinness on the way home. But when he's the head brewer, I guess he can do whatever he wants. But even so, apparently the experiments were slow moving. So he couldn't get that many samples. So he just tried replacing, as it was done at the time, sigma with S. And it really didn't produce accurate results. The smaller n is, the worse it got. And that was a problem. So he came up with a plan, and he did a lot of work on it, and he couldn't really use the Z, but he came up with a similar distribution called the T distribution. He had to call it students due to copyright situations. And so, yeah, it didn't come out till later amongst the general public that he had actually done all of this. But anyway, he wrote it under the pen name student. And we could take a look at it. In fact, I've got it punched up over here. The other book is still good for something. And they do have a few properties, which we'll get to in the other book coming up. But here's some of the pictures that we see. And compared to the Z-curve. The Z-curve is a little bit spikier. It's a little bit more pointy, centered at Z equals 0. Now, the funny thing is, T and Z carry many of the same values. When T equals 0, that's the mean as well. But we do have differences depending on what n would be. Now, as it turns out, this is actually n minus 1. We'll get to that in a minute. So if n was 26, this would be called the T25 curve, which is just a little bit lower than Z. And already, even at 25, it's starting to become pretty close to Z. But if you only have 6, called the T5 curve, by the way, then it's become even lower. You get down to n being very small, like 3 or 2 or something like that, then it's becoming more of a pancake squished situation. And a side effect of that is when it has a lower center, it gets wider tails, fatter tails, as they say, a mathematical term, of course. And the probability of what's under the curve always is 1. That is always the case, no matter what curve you're looking at. Probability must add up to 100%. So we do have that as well. So anyway, I just thought I'd show you the picture. I was frustrated by the fact this book doesn't seem to have any, at least none that I've found so far. And so that's certainly an issue. But anyway, I'd show you that, and we can get back to that as need be. But let's continue with the description here. And so up until the mid-70s, when some statisticians used the Z distribution, approximation for large sample sizes, and used T, which was done by tables, for sample sizes of at most 30. But of course, nowadays, the practice is to typically almost always use sigma. Unless your n is extremely large, then frankly, it doesn't make any difference at that point, unless you need 10 decimals of accuracy or something. But the nice thing, although what we have here, if you draw a simple random sample of size n from a population that is approximately normal, mean is mu, and an unknown population standard deviation, we use S instead. See if I can zoom in on this. It looks very much like what we just learned about Z. Z was still x bar minus mu. It did have a sigma over square root of n, but since we don't know sigma, we must use S. There you go. Sigma always goes with Z, and S always goes with T. It's just that simple. S means T. Sigma means Z. That's it. Write it down, memorize that, and you won't have to worry about it. There's n minus 1 degrees of freedom. Okay, well that's a technical term. We don't need to spend a lot of time on that, but for whatever reason, they've always decided to have our tables in terms of n minus 1. Okay, that's just the way it is. Chi-square does the same thing. And it has the same interpretation as the z-score. It measures how far x bar is away from its mean. And for each sample size n, there's a different student t distribution, as we tried to show you earlier. Okay, there go some of the deviations is 0. So anyway, you can find the last deviation once you know the other n minus 1 deviations, and then the last one is locked down. So if you know the average and you know like 4 out of the 5 values from only a sample of 5. So you got A, B, C, and D, but you don't know what E is, but you do have the total and the average. Then you can back into what E would have to be. And that is part of the theory for forming what is called degrees of freedom. Not just n, but n minus 1. I'm only the messenger, sorry. Okay, the graph for the t distribution is similar as we just saw. The mean is 0. This distribution is symmetric, of course. It's just a little flatter than z. And the smaller n is, the more flat it actually becomes visible there. But if you're doing sketches, which I hope you will, I will not notice any difference between a z and a t. They will look identical to me. Do not go out of your way to make the t look extra flat. That is not necessary. And of course, yeah, we have fatter tails here. There's more probability in its tails than z. The spread of t is just greater. It's a little bit more wide than before because S is more uncertain than sigma is. S has more uncertainty. Sigma is locked down, so there's less uncertainty there. So it's a little bit narrower, a little bit more precise. So if you do have reason to use a sigma and Z, you should do so. They're imploring you to think twice about it because it's not usually done. But I did it when I worked for the Forest Service. I guess that was back in the 90s. Well, anyway, the exact shape of the student's T distribution depends on degrees of freedom. We looked at a couple of those. That's fine. And yes, looks like I'm running out of battery again. So excuse me one more time. I have to get the plug. Give me a few seconds. Okay, I apologize for the delay. I should remember that. Every time I do back-to-back lectures, the battery dies. So um, most of this is pretty routine. T is very much like Z. And yeah, if n is very large, then T really just becomes Z. That's why in the past they used the approximation much more often than they do now. But if it gets beyond 1,000, there's hardly any reason to worry about T. And they even have an inverse T command on the TI-84. And you'd have area to the left, that's cumulative area, followed by degrees of freedom. So you've already had to take n minus 1 already. You have to do that yourself. Calculator won't do that. And by the way, the TI-83, which is what I have, does not have that command. It's a little harder to pin that one down. And there's a table, and I will show you the table right now. We do have a table available, and maybe some of you will even use it. I suggest you at least give it a try, even though you may not depend on it. So we have the shaded area alpha. So this is like the T notation is like the Z notation. It's not cumulative, it's the right-facing area. And then we have what's called they call it nu, Nu. It's a Greek letter N. It looks like a V. But that's the degrees of freedom. So they've already calculated it on this table, by the way. Some tables don't do that. Well, this one does. And so we could see certain examples here. For a 0.025, which is very typical of a 95% confidence interval, it may be, say, n is 10, so that means nu, or n minus 1, would be 9. This would be, if there is a popular value of t, that might be it right there, 2.262. T is typically reported to 3 decimal places. Now this table is kind of all over the map. There's a value, 636.62. You're not going to find that on a Z table. And T's, well, Z ranges between about minus 3.5 and plus 3.5. T will stay usually between plus or minus 4 most of the time, but if you only have 1 degree of freedom, that is, your sample size is only 2 back here, then the numbers do get to be rather large. But I'd say it's rather unusual to be using this top line anyway, the top row anyway. But we can get potentially some very large values of T. But if you look at the center part of it, all these values are pretty typically found just like Z's are. But there's one major difference. This is meant to be only highlights of the Z, well, in other words, as compared to Z, that covers all kinds of ground. For a single situation, Z does not need degrees of freedom. It just doesn't need them. So T does. And so we have several layers of several different different types of T distributions, several of them, about 40 of them or so. And then they pick the various alphas of some concern and they give you selected values of them. But if you somehow needed an alpha 0.07, you would have to get that from technology. The table wouldn't be able to help you. Or 0.04, couldn't get it. They only give you the major ones, the ones that they think are used the most. Although I haven't had any occasion to use that far right column at all. And by the way, when you get to infinity, that's code for Z. And then we see some values we've run into already. 1.645, 1.96, 2.33 often, but 2.326, and then even 2.576 is another very popular one. These other two are not very popular. 1.28, I've even seen that one used a few times. So at the bottom, it really blends into the Z. And even at the highest value they list on this particular table, 120, those values are very close already to the limit of Z. There's not too much to choose from. But with the technology available, may as well use it and get a slightly better answer. Why not? Okay, so let's see here. I was not able to get the table from this free book. I don't know what happened to it. So if you are looking for a table, you'll have to use the table from the other book, I'm afraid. But if you're using the calculator, you will only have a minimal use for the table. I just want you to get some kind of an appreciation for what the values are and where they come from and all. Anyway, if you have a sample size of 20 items, degrees of freedom, we'll talk about a tough formula. You better put this one on your formula sheet. 20 minus 1. It's 19. Breaking news. How about that? And you could even say T sub 19. Yeah, that says that's the degrees of freedom. They're not too interested in the sample size here. I think you're getting that picture here. They're interested in n minus 1. It's just the way it's done. Okay, and all this stuff, and we have our bounds for the population, for the confidence interval that we're going to try to also get going. And notice the only real change is z is replaced by t and sigma is replaced by s. And this is a lot more realistic than the other one that we talked about, which was a little bit easier to do. This one is actually more realistic and used a little bit more, quite a lot more actually. And even so, we're going to still add and subtract that error to our x bar. Now they have some instructions with the TI and all, and let's see if we can run through this one. Getting about halfway through this particular section. And let's take a look at this particular example. It's a study of acupuncture to determine how effective it is in relieving pain. You measure sensory rates for only 15 subjects with the results given. And so we can use this data to construct a 95% confidence interval for the mean. And we look at the data, and they do have the data here, but they've already calculated the mean. Thank goodness. So there it is. They got 4 decimal places for you. They even calculated S, the sample standard deviation, about 1.67. They didn't put any commas in there. I guess that's okay. Degrees of freedom, 15 minus 1. There it is. And so alpha, of course, for a 95% confidence interval, the reverse of that is 5%, 0.05. And then if you're going to use the table, you would need to know this. You'd have to have a 0.025 involved. And the other one would be 0.975. So just to quickly look at the table over here, which is really over here, we're looking at what's in the right tail. And so that would be one way of getting the alpha going, alpha over 2 in some cases. So anyway, let's see what we have. So alpha is 0.025, and so the area to the right is 0.025. That corresponds exactly to the table, and we would not actually need this value, but except for the calculator. Apparently the calculator will want to face to the left. I wish they could get on the same page. That would be so nice. But keep in mind, the statistical notation beat the calculator by several decades. Although statistics is considered to be a newer branch of mathematics, compared, say, to the Pythagorean theorem, thousands of years old, statistics mostly only got really rolling around 1900. So, I mean, it's been around, but it really started kicking in and going into overdrive just over 100 years ago. Dominated by British and Indian people, by the way. I thought I'd notice that because when I went to UCR, the entire staff was made up of Brits and Indian people. And they were all excellent. They spoke English far better than I do. I was impressed by that. Well, anyway, get some calculations going here. We want to find the t-value, and apparently that value is 2.14. They have decided to use the calculator. Let me see if I can find it on the table, just in case you need to use that for some reason. 0.025 is over here. We had 14 degrees of freedom. That gives me 2.145 as I'm circling it with my cursor. And how does that stack up versus what they got? 2.14. So apparently that was a rounded number. Don't ever round a rounded number. So apparently it rounds down. And I'm used to using t to 3 decimal places, so this rubs me a little bit the wrong way. It's the first book I've ever seen that uses t with 2 decimals. And I've taught out of dozens of books, and I've always seen 3 decimals. Of course, with your calculator, you'll get almost an unlimited supply of decimals, even more accurate than this. But the error looks like it's around a 0.9 or so. And so as you take the mean and add and subtract, just like you would with z, very much a replay of before. And here's the mean, 8.2, plus or minus about 0.9. Not surprisingly, you get to about 7.3 on the low end and 9.15 on the high end. And that is your confidence interval, for which you will be 95% confident that the true population mean in the long run would land between those two bounds. And yes, of course, the calculator has a little bit of a different point of view. Stat, then test, then t-interval. Press enter or press 8, I guess, and go to the data. You could type in the data if you'd like. And here, the C level is very easy. You just type in the 0.95. You don't have to take any alphas over 2 if you're using that type of situation. And then you get 4 decimals or even more of accuracy, and that's verifying what we said. And yes, the probability table could also be used. And yes, I've just taken care of looking at that. Looks like we're at about the 1 hour mark, which is usually my target for stopping. So I think I will end it here. I'll be giving you some WebAssign stuff. Looks like we'll still be kind of locked into using the book for problems, but since they're generic problems that work for any statistics class, I'm not really worried about that. So I will stay away, as always, from the most difficult problems, but yet I still want to challenge you. But they shouldn't be much more different than what we've just seen. So keep an eye out for that. I hope to get that out pretty quickly for you, and we'll talk to you once again live next Wednesday, and that'll be, what day is that? The 24th. 24th. So we'll be back live on Wednesday. We'll continue this topic, the t-distribution, and go into some other topics. In fact, over here, we can kind of see where we're headed. We're going to go for proportions, which is also the z-distribution again, and we'll maybe take a look at some of these examples. But lo and behold, we'll be done with this chapter pretty quickly. It's pretty short as far as I'm concerned. Looks like there's nothing terribly new about these 3 sections here. And then we'll try to get a little bit into hypothesis testing. That'll be upcoming in the near future. Okay, so we'll talk to you soon. Have a nice weekend, or have a nice few days here if you're watching this on Monday, which is the scheduled day to watch this. So we'll talk to you soon. Bye-bye.